Let's get started. Can everyone hear me? Okay. All right. So let me just go over a quick recap of a few things from last time, just to refresh your memory. But the two problems that we'll be focusing on today that I introduced last time were PCE, or the permutation code equivalence problem. So this says if I'm given code generators, let's see, G0 and G1 over a finite field, FQ. Your goal is to decide if there is a way to permute the coordinates of G0 to get G1. So this means, can I find an invertible matrix S and then a permutation matrix P such that S times G0 times P is G1, right? Okay, so remember that these two generate a code. So in particular, this is telling me that I have two codes that are equivalent if I can find anything of this form. And recall that codes look like this, right? For generator matrix G, they are this set. Okay. All right, so LIP, the lattice isomorphism problem, was very similar. And this says the following. Now I'm given description of two lattices, so they're bases. B0, B1. And now your goal is to decide if there is a unimodular matrix and an orthonormal transformation that takes one to the other. So if I can find a unimodular matrix and then orthonormal. So very similar equation for these, for any equivalent lattices, right? Okay, and just to show you the parallel, lattice generated by a basis B has this form. Usually we use columns in the lattice world. That's why I'm writing it like this, but equivalently you can do rows for both. So we have this, right? So we saw last time a bunch of reductions between variants of code equivalence and the lattice isomorphism problem and other isomorphism problems. So how hard is it to actually solve them? So for that, I showed you this list of algorithms, right? So these are the best algorithms we have for solving these isomorphism finding problems. So for GI, I didn't recall it here, but if you remember the graph isomorphism problem, this has the fastest, best known running time out of all of them. And then these are all exponential for LCE, depending on whether you want deterministic, randomized, quantum algorithms, all that. And then LIP, we don't know of anything better than this, right? So this is the map of reductions that we saw last time. Oops. And gives us an idea of like how hard all these problems are relative to each other, right? So, okay. But how hard, okay, so I showed you how hard these are relative to each other, but how hard are they actually to solve in the grand scope of things? So there was a work by Petrank and Roth in 97, and this showed that the code equivalence, but in particular they showed it for PCE, is unlikely to be NP hard. NP hard to NP complete, actually. So let's take this apart and I'll tell you what this means. But For a problem to be NP complete, this means that it has to be in NP, right? So in the class of all problems that I can verify the solution efficiently for, right? And it also has to reduce to, any NP problem must be able to reduce any NP problem to it, right? So for any problem, let's see, P, bad choice. In NP, I must be able to reduce this to this. Okay, so basically what this tells me is that if I have any kind of solver, if I have any kind of solver for this problem, then I can use it to solve any other problem, right? Actually, I think these are switched here. It should be the other way around. Okay. Let me just write NP hard. All right, so this is what it means to be NP complete and unlikely. So what they actually show is that if PCE is an NP complete problem, then this assumption doesn't hold. And the assumption, just for completeness, is that the polynomial time hierarchy collapses. Okay, so I won't go into what this is, but basically it's this, you can define a hierarchy of problems depending on what problems have access to what oracles, and you can define this entire hierarchy of problems in P space, in the set, over the set of all problems that can be solved with polynomial amount of space, right? So it just generalizes the complexity classes of NP and its complement co-NP. So for it to collapse, it means that you find that problems between different levels of the hierarchy are equal to or equivalent. So yeah, it's widely believed that this is not the case. So that's why we say that BC is unlikely to be NP complete. Okay, so in summary, what I'm trying to get at here is that the code equivalence problem is not too hard, right? So it's not NP complete, but it's also not too easy to solve, right? Because these are the best known algorithms that we have for them, right? And this problem has been here for a while, so it's reasonable to assume that we don't know, we don't know how to do better. Okay, so this result here actually holds for any isomorphism problem, not just PCE, right, or code equivalence. Okay, so I want to give you an idea of like their proof. So they rely on a couple of major works, but the core of their idea is this interactive proof for non-isomorphism. So if I give you, so what do I mean by non-isomorphism? If I give you an instance, so let's say I give you two generator matrices, G0 and G1, such that their codes, right, are not equivalent. So up to permutations, right? Let's phrase it for permutations here. Then I want you to prove that this is the case, right? So this is the idea. If I have a prover, let's say the prover has unbounded computational power. It can do anything it likes, but it has to prove to a verifier, which is polynomially bounded, right? It can only check up to so much, that it knows that this is the case, right? So here's what it does. the verifier is going to flip a coin and then choose one of the two generators. Okay. So then it's going to randomly sample a new generator matrix, H, from the class. So I'm denoting it like this, just for shorthand, but I'm looking at all the possible codes that are permutation equivalent with this GB that I chose, right? And I'm sampling a random one, and I'm going to send this random H to the prover. And now the prover's goal has to decide what B was, right? So I want to find this B and guess it, right? So if you look at this, the prover can just randomly guess, right? Can also flip a coin in 50-50 weighted coin. And if it happens to be right, then sure, it can convince the verifier with this one round, right? Does everyone see that? But it's much harder if I iterate this many, many, many times, right? For the prover to actually convince the verifier that this is the case. So okay, so in particular, repeating by m times, we get that the probability that the verifier is convinced, so it's about, okay, 1/2 to the m, right? If the prover is just guessing randomly, right? But it should succeed with overwhelming probability if it actually knows that if it can actually show that these are not isomorphic to each other. So this is the core idea. And also I'll be showing you a few interactive protocols similar to this, like all throughout. This is the base of a lot of the cryptographic schemes that we're seeing. Any questions so far? Okay.
I have a question not directly related to that, but the map you have above, you have that SPCE is reduces to LCE and vice versa. Last time you only had one of those directions.
Yeah. So, well, okay, I won't pull up what I had last time, but there are two separate works. So this was the original one from SPC to PC by Dukas and Gibbons. And then this one here is a CARP reduction from some previous work. So the map is a little bit misleading because like you have these back and forth arrows, which may tell you that these are perfectly equivalent to each other, but the run times of the reductions also matter here. So in particular, like these two have very different, they're still polynomial, but there's differences. I don't know if that helps answer.
Well, last time between SPC and LCE, I believe I asked you why you didn't go both ways, and then I thought you said there wasn't a CARP reduction between, I think, LCE to SPCE.
LCE to SPCE. Yeah, this thing, I think this here is a Turing reduction, as far as I remember correctly. Yeah. Yeah, so misleading both in terms of like Turing and versus CARP, but also the runtime of the reductions. Yeah. Okay, any other questions?
Here the prover can decide because maybe about you.
Yeah. 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 Back there.
Maybe it's a dumb question, but what's the hard problem that we're reducing to an easy problem by doing this?
So, yeah. So the proof is actually much harder, and feel free to jump in, JF. But it's, so basically the proof says if I can show this interactive proof of non-isomorphism, then I can plug it into this general framework that tells me if I can do this for a problem, so I'm not reducing to anything. If I can do this for a problem, then like I have this statement here, right? So it's like any problem for which you can do this, like I'm not reducing to anything, any problem for which you can do this, satisfies this condition. Yeah. Okay. But we will see protocols that rely on problems being hard. So yeah, that's next. Okay, all good? All right. So the first crypto system I'm going to show you is CE based. So okay, so I'm going to claim the following and show you an example, but if I take any problem, so not just CE, but any problem that's formulated like this, where my goal is to find a secret group action oops. That transforms one object into another. Then I can use this for crypto, right? Okay, so this includes all variants that we know of for code equivalence, right? So I have two objects, two codes in my case, and I want to find the group action that transforms one into the other. And I'll show you an example later, but first I want to show you the general framework. So at the bottom of a lot of crypto systems is this zero knowledge protocol. So zero knowledge proof. I'll explain the terminology a little bit later. But basically you have some public parameters and some private ones. I'll write it like this for now. So I know the two objects, C0 and C1. I know a group, right? And I also know an action. But I don't know which group element is the one that transforms C0 into C1. Okay. So the zero knowledge proof, again, is an interactive protocol between a prover and a verifier. And now the goal of the prover is to prove that it actually knows the secret group action without revealing it to the verifier, right? That's what makes this protocol zero knowledge, because the verifier doesn't learn the secret, it just is convinced by the end of it. Okay. So here's how it goes. The prover is going to sample a random group action from the same group. So for the same group, it's going to define a new object using this by applying this to C0. So just one of them, it doesn't really matter. It's going to send this to the verifier, and the verifier is going to flip a coin. So it's going to choose one of the two public objects, and it's going to tell which one it chose to the prover. And now, if the verifier chooses the first one, 0, then it's going to send this. Otherwise, it's going to send this. So G tilde, G inverse tilde. All right. And then the verifier is going to check if I act on CB, the object that I chose, with the group action given to me by the prover, and I get the random object that was sent before, then I'm going to accept, and then otherwise reject. Okay, so here's what I want you to see here. CB, so one of these two, yeah. So flipping B, and this is the one that the verifier chooses, yeah. So what I want you to notice here is that the prover, it has access to this secret group action G, little g, right? But it's not actually revealing it to the verifier at all. It's masking it with this random group action, right? So never, in either of the cases, does actually reveal information about G. So that's what's making this zero knowledge here. And then another thing that I want you to note, so usually this object isn't sent just in the clear completely directly. Usually you commit to this object using a hash function or something else to make this smaller and make communication between the two parties efficient. But I won't go into that. I'll just keep that in mind for all future protocols. Okay, so here's the idea, which hopefully should be clear by now, but I know how to get from C0 to C1, or the prover knows how to get from C0 to C1 via G, but I basically have this diagram. I think these are switched, but yeah. Right, so this is what's being used here. I can get from one to the other just by using this alternate route. Okay. So this is pretty easy to check. I can just check it for completeness, but for B0, hopefully it's clear. For B1, note that the verifier is going to get this. This is what it's checking. It's going to check that this acts on G star C0. And this is exactly, so these cancel and you get this. Right? So, yeah. In both of these cases, the verifier will accept if the prover is doing everything correctly. Okay. All right. So the less signature scheme uses this idea, but the group action that they are concerned with is scaled permutations given by monomial matrices, right? So LCE based. Okay. So let's take this apart again. So for those who are not familiar, signature schemes are used to authenticate documents, right? So if you want a way to, for a document to be authenticated by an authority, so to be able to sign electronically, right? You want only authorized parties to be able to do that, but you want everyone to see the signature and be like, okay, this is a valid signature. So everyone to recognize that authority. So formally, this is specified by signing algorithms and verification algorithms. So I need a way to sign, and signing is going to be done with a secret key. You can only sign if you have access to a secret key. I'm going to sign a message, whatever document I'm given. So I'm going to produce the signature sigma. And then to verify, anyone must be able to do this, so I have to use a public key. And I have the message in the clear and the signature, and I'm just checking that this sigma is valid, but valid for M. Okay, so just a side note, this like the messages are in the clear, right? Like this is not a way to hide messages to communicate, right? This is not an encryption scheme. It's just a way to sign and verify in a globally recognized way. Okay. And in order to be able to specify what the secret key and public key are, I have to be able to generate it too. So I need a generating algorithm that sets everything up for me. Okay. So only authorities can do this, and then anyone can do this. Okay. So this is the basic structure, and I'll show you exactly how these algorithms work later. But we build this starting from the core, which is our zero knowledge protocol, based on LCE. So here's what we do. This is step 1. So I can just instantiate the same framework I had before. Whoops, it's over here. So this same framework that I had, I can just instantiate it with scale permutations given by monomial matrices. So in particular, let's see. In particular, okay, I have to specify what codes I'm talking about. My objects are codes, C0 and C1, and then my C0 is some monomial matrix, like acting on C0. So these are an FQ to the n. Okay. And what's secret here is this group action. Right? So I'm abusing notation a little bit here, but just to give you a general idea. Okay. So the idea for this is same as before. The prover knows how to get from C0 to C1 via M, but it's going to show, it has 2 cases, just as before, right? It's going to hide what it knows using this randomly selected group action. So here, I'm randomly selecting this M tilde. That's going to take C0 to some C tilde. Oops. And I can also get there by doing M inverse times M tilde, right? So this is, these are the 2 group actions that it could output, right, in a given round. Okay. So, yeah. Does this idea make sense? Okay, then I won't write it out for this, but. Okay, so same as before. So if you look at just this general framework here, same as the other interactive protocol we saw, the prover, if it just flips a coin randomly, it can convince the verifier, right? So we have this same need to repeat the zero knowledge proof many times, right, to get a certain security guarantee. So what I'm going to do here is repeat this whole thing m times. And by doing this, I get something called an identification scheme. Okay. So, and again, just to clarify, in repeating m times, I don't have to go, okay, there's a way to phrase this where I don't have to go through this game m times, like over and over and over again. I can do it in parallel and just say, sample m of these. Do this m times, send all m of them to the verifier, the verifier flips m coins, and then for every single one of those coins, you do this, right? So yeah, it's all packaged, and then the verifier only accepts if every single check passes, right? So that's how you get the overall proof. Okay, so to take this identification scheme, so we went from zero knowledge proof to this identification scheme by repeating. I want to actually take it to a signature scheme, and there's a standard way to do it. So it's commonly used. It's called the Fiat-Shamir transform. So Fiat-Shamir, they showed this method of transforming any interactive identification scheme into the signature scheme that's non-interactive, right? Right, so remember here when I gave you a general template for the signature scheme, there's no proof, there's no communication between two parties. It's just a way to sign and a way to verify. So this is my end goal here. So I won't show you what they do, but if you apply this as a black box, then you can get the following. So I'm applying it now to my identification scheme that I got before. So to sample my public key and my private key, I'm going to sample this monomial matrix. And I'm going to also choose a code. There's multiple ways to write this, but you can have the generation algorithm just give you the code and post it publicly. And then I'm going to compute this new code by applying M to C0. And I'm going to set my public key to be this pair of codes and my secret key to be this secret monomial, right? The secret group action. Okay. Now to sign, I do the following. So I'm going to sample a bunch of random monomials, monomial matrices, M1 tilde all the way to MT tilde. Then I'm going to compute the C tilde, so same thing that we saw from the protocol. But I'm going to compute T of these by applying these M tildes to C0. Okay. All right. Here's what we're going to need, and I didn't mention this before, but in addition to all this, we need a hash function. And I'll explain why. So in particular, I want to be able to hash anything, no matter how long it is, to this bit string, this T-length bit string, right? And I'm assuming throughout that this is a cryptographic hash function, which means it's collision resistant. It's really hard to find two things in the domain that map to the same output, right? If that happens, if I can do that, bad things happen. The things can break. Okay, so here's what I'm going to do. In the signature scheme, I'm basically trying to mimic the parts of both the prover and the verifier. So remember, the verifier was flipping these secret coins, but now I don't have this interaction. I have to generate this random bit string somehow. So I'm going to use my hash function to do it. And the seed to this hash function is going to be my message. So I'm going to compute these bits as the verifier would, but I'm going to use this hash function and give it whatever I generated here and the message. So here's where I'm using this secret message, or sorry, here's where I'm using the message, but this function here is public knowledge. So anyone with access to the message and this input can compute it, right? So we're going to use the secret elsewhere. Okay, so these are bits. And I'm also going to generate the responses like I would. Okay. I'm going to choose let's see. Okay, so same as before, for a given bit that I have, so now I'm looking at every ith bit. If it's 0, I'm going to just use my randomly chosen monomial matrix. Otherwise, I'm going to also factor in my secret key. So this is where I'm using the secret key, right? Okay, and then I'm going to output all this information. So this is the signature that I'm generating. It's all these generated codes, C1 tilde through CT tilde, and then these actions. Okay, so yeah, all right. Let me first show you the verification. So here I want to be able to use my public key to verify that the given signature is valid for a given message. So to do this, I have to basically recompute the bits, right? Because now I'm like, there's no verifier giving these bits to the prover. The prover kind of has to compute it again. So this is what the sign and ver algorithm are simulating. So again, I'm going to hash whatever is in the signature. So this C1 tilde, this is all in the sigma. And I'm going to use my given message M. And then I'm going to accept if and only if this condition holds for every I. Okay. All right. Does this make sense? Okay, it's a bit long, but it's important that you see it for the next one too. So one thing I wanted to note is, like, if you look at this signature, it looks really big and clunky, right? Like, these things are all describing codes. So they're generated by these huge matrices, K by N matrices, and there's T of them. And then this is also describing some kind of group action, like T group actions, right? So to represent this, it looks really big, but we can compress the size of the signature down by hashing. So I'm not going to show you optimizations throughout, but it's possible to reduce the size down. But morally, this is what the signature is composed of. Okay. So this is how the less identification scheme works, and I should have, yeah. Okay, so for the less identification scheme, just a note, so this is the basic idea of how it works, but like when we actually choose the parameters, like when we actually choose these parameters and, you know, and everything, we have to, sorry, when I choose like the field size and the block length and like all these parameters, I have to keep in mind like all possible ways I can attack the underlying problem, because everything here is built on this, that I cannot, just by knowing C0 and C1 and some like random things in the public group that in the public group that I have and the spaces that I have, like I cannot reconstruct M, right? That's the LCE problem. So this is the underlying hard problem. So in order to make sure that this whole scheme is secure, I have to choose my parameters pretty carefully. So the way they do this is they look at all known attacks based on solving LCE. So these work in two ways. I'm not going to write them here. But one is to reduce LCE down to PCE, so reduce it to just, permutations, or to find low-weight code words. And if you can find low-weight code words in your code, in your pairs of codes, then you can reconstruct the secret key M. So that actually uses collisions, or it allows you to find collisions in the hash function, essentially. So one outcome from all this is that they usually take the field sizes to be at least 5. But that's just because we don't know of efficient algorithms that can break LC for greater than 5. Any questions about this so far? Yeah.
So our public key, C0 and C1, is this not adjusted by the hash Gaussian?
Sorry, can you repeat that one? Is it not?
Our Gaussian hash is like
E
Is it not problematic to exclude the public key, or is it fine?
Wait, you're excluding the public key. I'm not sure I understand. So this public key here, like I'm excluding what from?
Yeah, so that's not part of the hash in Gaussian.
Oh, I see.
Is that, like,
see.
I'm genuinely asking because I don't know. Is that problematic or is that fine?
I don't know. I'm not entirely sure. But if I understand correctly, like, these are both built under the hood. Like these are under the hood in the hash that you're using here, right? And like this is publicly known, but just because you're sampling these randomly, like these are also just random codes. I don't know. Does anyone? Okay. Yeah, maybe you can let me know. Okay. All right. So let me move on to LIP-based cryptography. So now we're switching tracks from codes to lattices. And again, I'm going to show you a signature scheme. So, okay, actually, let me backtrack a little bit. So remember that in the less signature scheme, this was LCE based, right? It was based on this code equivalence problem by plugging it into this general framework that I had, right? I plugged it into this kind of core, this zero knowledge proof, where I could have put any kind of isomorphism problem of this form. I could also do that for LIP, right? LIP is also a problem of finding isomorphisms between lattices. And you can define group actions on them, right, in the same way. If I do this for LIP, that's actually a bad idea. It works and everything, but the problem is the representations of lattices and everything that you would get from that signature scheme is huge. So it just blows up. So that's why for LIP-based crypto, we do something a bit different. We don't use that framework. So in particular, there's this Hawk signature scheme. Okay, and this was, I should have mentioned the authors earlier, but this one is by Dukas, Postlewhite, Polis, and Warden from 22. So it's a very recent proposed signature scheme. So this is actually a NIST submission, which is also why it's an object of interest. So and it uses the following kind of idea, which is not the first of its kind. It's a very old idea. So to make a signature scheme, you can use this hash then sign design. we do the following. So if let me actually find I cheated a little bit. I did not want to draw all this. Okay, so basically, if I have a lattice, so that's what I'm representing things as, I know a public basis, right? So a basis for this lattice could be something like this, B1 and B2. I'm only going to do two-dimensional lattices. But there are nice bases for this lattice too. So like this one, right? So the idea for hashed and sign is that I can, in order to sign any message, I'm going to take whatever message I have, and I'm going to map it into a target. So I'm just going to kind of encode it into a vector in this space, Rn, using a hash function. And then I'm going to use, let me actually bring it here. I'm going to use this nice basis that I have, this good short basis, to find a lattice point that's closest to it. So let's say I could find this one. And this is what I'm going to choose for my signature, right? Okay. And then to check that these actually match, that this message and signature pair match, is to check whether these 2 points are close to each other, right? And that my signature actually lies in the lattice. So this is the idea, the general idea. Okay. But how do we actually make this hard for people who don't have the short basis to do? So let me show you again. Okay, so let's say I have this lattice, and I know a good basis for it, right? Okay. But if I only have like a basis that's really, really long, like this really bad basis, let me change it actually, something like this. And okay, so I'm telling you this for now. I'll explain why these are good and bad bases later. It all relies on algorithms we have for solving these problems. So let's say I have this basis, B1 prime and B2 prime for this. And I can actually say that in order to go from one to the other, I just need to apply this unimodular transformation. So if I keep this secret, I can use this as my secret key and then post this bad basis publicly. So this becomes my my public key, right? So why do I want to do this? If I only know this bad basis for my lattice, then it's actually hard to go back and recover a nice short basis from it. Because basically what you're doing here is solving the shortest vector problem, right? Okay, so here's why bases can be good or bad. If I have a good short basis for a lattice, then my fundamental domains that are, that correspond to this basis are nice and round. Otherwise, they look something like this, and I'm going to mess this up because these are super elongated, but something like this. They should not contain lattice vectors. right? So they're super, super elongated. So if I'm using this idea where I want to basically take a target and then find the closest lattice vector to it and use that like as my signature, it's much harder to do for bad bases. So in particular, there's this algorithm called Babai's nearest plane algorithm that for any target T that I have, so if I have a target T, it will decode to the nearest lattice point. So it'll succeed in decoding to this nearest lattice point if I have this nice round fundamental region, right? But if I have something like this, if I only know this basis, then let's say some T here that still lies in the fundamental region, right? It could look much closer to this lattice point, so the wrong one, right? I want to get the center. This is my goal, even for this, right? So if Babai's nearest plane algorithm knows a good short basis, it can do this very easily, but this, it will fail, almost certainly, right? So that's why using this trapdoor short basis and keeping it secret, and by transforming it into this really, ugly, bad basis, this is why you're not really revealing this, right? It's really hard to go from here to here, and it's also like really hard to use this bad basis to actually get what you want easily, right? That's the general idea. Okay. All right. So if you look, this is kind of starting to look like LIP, right? I took this lattice basis B, and I transformed it with a unimodular transformation. But to make it truly LIP based, we do the following. I not only need to transform it this way, I also need to transform it with an orthonormal matrix, right? So what I'm actually going to get is something rotated, whatever rotated version I have of this. Okay, it's probably wrong, but yeah, this is what it looks like. So what I now have here is our LIP equation, OBU, right? Okay. So this is the idea that's used by Hawk. But there are two problems with this. If you look at a lattice, right, you're describing a discrete additive subgroup of Euclidean space. So everything here is represented with real values, right? So if you represent things with real values, to actually put this into practice, you need to be able to represent things using floating points, which suck to deal with. So they avoid that in a certain way. But not only that, there's another problem in that when we generate the secret key, whenever a signature scheme generates the secret key, you need to be able to sample these efficiently and in a way that doesn't leak information about your secret trapdoor lattice, let's say, right? So to do that, you have to be able to define random sampling for these infinite sets. So this, right, we need a well-defined notion of efficient random sampling. So what they do is actually they shift everything and rephrase everything into quadratic forms. So okay, so for a basis B, I can define the Gram matrix of the quadratic form like this, B transpose B. And then any lattice that I have here, right, this is in real space, and then I have this inner product. But when I move the quadratic transforms, the lattice is always Zn. And now the geometry of my object is captured by the inner product, which is with respect to the quadratic form. So basically what I'm doing here is I'm abstracting away the exact embedding I have of my lattice into Euclidean space, and I'm only capturing the geometry. So that's what this does. So instead of here, representing it here, I represent it here. Okay, so I can formulate LIP in this way. It's equivalent. So given two quadratic forms specified by Q and Q prime, such that Q prime is U transpose Q U, I want to find U. Okay. All right, so basically I'm no longer dealing with orthonormal transformations, and here's why. Any quadratic form that I have is invariant. Right, under anything from any orthonormal transformation. So if I have this, let's say I have a lattice basis B prime, that's equivalent to the one B that we saw before, then I can define this new quadratic form from it. If I take the transpose of B prime and B prime, B prime transpose and B prime, I get this. Okay, so this always cancels out, right? And I'm left with just this. Right? So this is now basically reducing everything to only caring about the unimodular transformations. So this is great for representation purposes because everything here is in terms of integers, right? All my matrices are now integers. Now we also have to define some kind of notion of random sampling. The way they do that is using discrete Gaussians over the equivalence class. I won't go into it because I think we're short on time. But basically, for an equivalence class of a quadratic form, so it's defined as like all the quadratic forms that look like this, that can be transformed, can be obtained from a Q. I'm going to define this distribution over it using the discrete Gaussian over Zn. And I can do this so that sampling from this distribution is efficient, right? So I solved the second problem that I had to deal with, right? That one of like, I can't really define a distribution over this infinite set of transformations. Okay, so now for the ZKP, the zero knowledge protocol that's at the core of this. It's again very similar in structure to what we saw before. So if I have this Q0 and Q1, which are public, and I know how to go from one to the other with this U, and I can randomize Q0 to get Q tilde, and also get here using U inverse V, right? So the same kind of idea works for the ZKP. I'm not writing everything out, but this is the general structure. And what allows us to actually do this is our nice sampler that we have. So we needed this sampler in order to define this zero knowledge proof. Okay. All right. So the signature scheme works now very similar to what I showed you before, where I take a message, right? I'm hashing it to something in my space, but now it's a little bit different. And then I'm going to take the nearest lattice vector, and that's my signature, right? But now I'm working over the integer lattices. the integer lattice, Zn. What they actually do in Hawk is a little bit different. They optimize things quite a bit for efficiency and to reduce the size of the signatures, and they use module LIP. So this is an equivalent version of LIP, but it's defined over module lattices. So they, in particular, take this a cyclotomic ring of power 2, and they take this module lattice R2, which is actually isomorphic to Z2M. So this is our new n here. So this is our rank 2 module. Okay, so there's a bunch more optimizations that they do, but this is the underlying thing they use. And one thing I wanted to note is that here, like this general framework that they have for using this quadratic form formulation of LIP and using this as a signature scheme, it works no matter what lattice I give you. It doesn't have to be for the integer lattice. They do this because it's simple and easy, and while still getting a signature scheme that's competitive with everything that exists, right? So it's still better than other lattice-based signature schemes. Okay. Yeah. So let me just end the security of it. So hopefully, so for security, LIP, so we're saying this is LIP based, but the hardness of LIP is what makes recovering the secret key hard, right? So same as I was mentioning at the very beginning here. It's hard for me to actually recover this because I can't solve LIP easily, like just given the public bad basis. Okay, and then because all known attacks against LIP, so all known algorithms that solve LIP, they require finding a shortest vector. So the fact that the shortest vector problem is believed to be hard, then I cannot actually solve LIP easily. Right, so this is what the security of Hawk is based on, basically these two hard problems. Okay. All right, I think we're out of time, so any questions?
Just some semantics. So here, is it really like LIP? Because like you're not giving me like the good basis and then the bad one, and you're just, isn't it just like?
Okay, let's see. So, okay, it is LIP based because here, so remember, so this was for any kind of lattice. I gave you just like any arbitrary lattice with a good basis and a public bad basis. But when we move to the quadratic form formulation, this basis is now known. Like I know that my lattice is Zn. Like, so this is now public, and this is also public now because I'm giving you, right, two quadratic forms. But this is basically the secret key. I should have clarified this before, but like this is our secret, not really the good basis anymore. Yeah.
Is there an instance of BDD somewhere?
Yeah, so
Signature is BDD, right? So if BDD was weak, we don't know how it relates to IP, do we?
no. So yeah, actually the BDD problem, so for those who don't know, BDD is the bounded distance decoding problem. It's an approximate version, approximate promise problem that's analogous to SVP. So basically, if I give you something, let me go back actually to here. Okay, let's do it here. If I give you any point here, and I'm guaranteeing that it's close enough to a point in my lattice, I want you to find my lattice point. That's what BDD says. So yeah, that's also used as the basis for this, because if we could solve BDD efficiently, then recovering a valid signature from a target point would be easy for us too. Yeah, so yeah, I didn't mention that explicitly, but it's there. Any other questions?
I have one more question.
Yeah.
So, you gave this general framework for like isomorphism problems, and like when you do this kind of, let's say, zero knowledge proof, like you're basically putting out like your secret times a bunch of elements, right?
Mm-hmm.
So, are there any settings where this is known to be like an issue, or we're generally not concerned? Like if somehow our groups you're working with were close to cyclic or something like that, that might be an issue. But like in general, there's no situation. Like, are people not concerned with leaking too much information if you have to run that several times?
Yeah, I don't think so, because also like, so I gave you the general framework here, but like in all these schemes, they choose the spaces very carefully. So they choose carefully like where they're choosing their codes from, like what lattices they're choosing. So Hawk actually, yeah, if you look at the Hawk paper, they break down like what happens if you use like all these different kinds of lattices. So yeah, for some lattices, for sure, like solving this problem would be much easier. But
What Vlad is concerned about is this revealing of the secret times random playing multiple times, right?
Yeah.
I
That's
see.
information here to they're carefully distributed uniformly at random. I don't
Oh,
think
okay,
you-
I can pick the, yeah.
Yeah, I don't think you're getting anything.
Wait, so okay, if I
G tilde times G inverse. Like your response in case of B equals 1.
right, oh,
That's
okay,
making you
yeah.
nervous that there is a G in there.
Okay, yeah, but this space is like, we're assuming this is really, really, really big, right? Where it doesn't matter how many random samples I have. So I can't recover this G. Is that what?
Typically, if you think
Right.
about something, you're
Mhm. Yeah.
Yeah.
Mhm. Okay.
No more questions? Let's thank the speaker.